In this video, we're going to go over a very common example for the gravitational force. In this example, we'll look at the satellite that is orbiting around the Earth and we'll calculate its orbital velocity and the period of its orbital motion. So let's examine this problem. A satellite of mass 200 kilograms is orbiting the Earth in a circular orbit at an altitude of 500 kilometers above the surface. Given that the mass of the Earth is 10 to the 24 kilograms, excuse my cursive, and the radius of the Earth is 6.4 10 to the 6 meters, determine the gravitational force, the speed of the satellite in the orbit, and the period of the satellite's orbit. So let's take a look at how we would solve this example. So the very first thing is, of course, we need to convert our units to standard units. So here we have 500 kilometers, which we should convert to meters. 1 kilometer has 1,000 meters, so I want to multiply this by 1,000, or essentially add 3 zeros to this number. We should strive to write our numbers in scientific notation, especially if they're really large. So I can write this as 5 and 10 to the power of, let's see how many zeros we have. We have 5 zeros, so it should be 10 to the power of 5 meters. Now, let me do a sketch for this problem. For any physics problem, you will basically always do a little sketch, right? Now, here's our beautiful planet and the satellite that is orbiting around it. Now, the only force that the satellite is really experiencing is the gravitational force, which we have to calculate in the first part. So gravitational force, the formula for it is G, the gravitational constant, times the first mass times the second mass divided by distance squared. Now, G is just a constant, 6.67 times 10 to the minus 11. M1 is the mass of the satellite, of course, 200 kilograms. M2 is the mass of the Earth, because that's the second body in this problem, the second mass. Now, let's talk about the distance, right? A lot of people make a mistake of putting 500 kilometers or even this number in terms of meters in for distance. But you have to remember that this D in this formula is the distance between centers of masses of the two objects. So we need to find this distance that is not directly given in this problem, because D consists of h, right? So it's height above the surface and radius of the Earth. So D is equal to h plus radius of the surface, where height is 5 10 to the 5, as we just calculated, plus radius of the Earth 6.4 10 to the 6, which simplifies to 6.9 10 to the 6 meters. Remember, remember, you can always switch your calculators, right, to scientific notation by going to mode and going to sci-fi. So selecting, there will be normal and sci-fi options. So switch it to sci-fi for the purposes of this problem. But now that we have this distance over here, we can plug this in, right? Plug all of this into our calculator and we'll find the gravitational force of 1,681.2 newtons. If you didn't get the same gravitational force, it is likely due to some error of you inputting it into the calculator. So just as like additional advice is that you can, to deal with these like really big numbers, you can rewrite it as 6.6 E, and the way you get to this E on the calculator is by clicking the second button, and above the 7 button there will be a comma, right? And on top of this comma there's E. So it's second comma button brings up E, and then just write minus 11, right? This is a kind of a calculator way of writing this number, and it will make your calculation a lot simpler. So this will be my advice if you didn't get the same question, didn't get the same number. Now let's take a look at part B. So calculating the speed of the satellite in the orbit. So just like all of the problems in this unit, I will start this problem by writing the second Newton's law. F net is equal to ma, right? The only forces we discussed that the satellite is experiencing is the force due to gravity divided by distance squared. Now, furthermore, the satellite is moving in a circular orbit, so we can plug in the formula for the centripetal acceleration. V squared over, so V squared over R, right? But the radius of the orbit is this distance D in this question. So we can simplify this equation a little bit. We can multiply both sides by D, right? And basically cancel out 1 power of D. We can also divide both sides by M, right? And we basically have G times m Earth over d is equal to v squared. And finally, since we're looking for velocity, right, or speed, we can take a square root of both sides to find the final equation for this velocity. All that is left is just to plug in our numbers, so stick with me. 6.67 10 to the minus 11. This would be, by the way, a good opportunity to stop the video, get your calculator, maybe practice putting in these big numbers. So mass of the Earth, right, is 6 10 to the 24. The distance is going to be the distance we calculated here, so 6.9 10 to the 6. And if you plug all of that into a calculator, let me calculate it, 7,615.8. Oh, that was some mental math I just did right there, wasn't there? Okay, so now that we did the speed of the satellite in orbit, just one last part is the period of the satellite's orbit. So if you remember our unit on circular motion, and if you don't, I would advise you maybe watch it again to review it, because the gravitational force and the circular motion are quite linked in a lot of the problems. The period velocity can be written as, so for constant motion, right, the velocity can be written as distance over time. And period is the time it takes to complete one full revolution. And one full circle is essentially just the circumference of the circle, 2 pi r. So here we have our equation for period of the motion. If you multiply both sides by the period, and you divide both sides, so again, I just basically multiply both sides by t. Now I want to rearrange this for the period t, so I divide both sides by velocity. And since I know the velocity from the previous question, right, I can just plug in my, again, the radius in this case is the radius of like the rotation. So it's actually going to be this d that we found right here, 6.9 10 to the 6. And the velocity is the one that we found in the previous question. And if we plug all of that into the calculator, we get 5,692.6 meters. All, of course, we're dealing with time, so it should be seconds. All right. So just like this, we looked over one of the most common problems in this unit. The best way to make sure you understand it is to try to solve this again on your own. And if some parts don't make sense, feel free to rewatch this video again. Hopefully that was helpful. Keep practicing and keep working, keep watching these videos